In this video, we're going to learn about code converters. So what's a code converter? So a code converter is a combinational logic subcircuit that does exactly that. It converts from one type of encoding to another one. So basically converts from one type of input code that you have to a different type of output code that you can assign or that you have. So some examples are the 3 to 8 decoder. In that case, you convert from a binary code to a one hot coding. In the 8 to 3 encoder, you do the opposite. Another common one is the BCD to 7 segment. Okay, and so first we're going to learn what is BCD. Okay, so BCD means binary coded decimal. So a BCD represents a decimal digit using 4 binary bits. Okay, so for example, if we have 1 in decimal, we have a 0001. If we have a 5, we have a 0101. And for 9, for example, 1001. So if we want to represent a 329, we use a 3, a 2, and a 9. So 3 in binary, 2 and 9, so 329. Okay, and it's not the same as having all of these together. In this top one, we have space right here and we have a space right here. Okay, and so we use this to drive 7-segment displays. Let's do an example. So we're going to design a circuit, a code converter circuit that drives a 7-segment display. The 7-segment displays has 7 LEDs, so it has the A, B, C, D, E, F, and G, and depending on which LEDs you turn on, that's the digit that you display. Okay, so you display from a 0 to a 9. So a code converter is this. This is the code converter circuit. So you convert from the 4 bits A, B, C, D. You have a different output coding, and in this case it's going to determine, and the circuit is going to determine and say when this A LED is turned on, when this B, the C, and so on. So for that, we always start with what? We always start with a truth table, right? So we're going to have a truth table for our code converter. So on the left side, we have our inputs, A, B, C, and D. So that's our first code. In the right-hand side, we have our outputs. That's going to be the code that we convert to. So whenever we have a 0000, then we can say my code is like a password that you're designing. Basically, you have a code, and then your friend has um, the key for that code, for example, and he can translate from one code to a different code. And so the converter, you have to basically give it the key of that code. So for example, in this case, we have a 0, and so to form a 0, I'm just gonna put it right here, right? So to form a 0, I have this guy, this one, that one, that one, and that one. So all of them are on except for the G, right? Correct. Now another example would be the 1. How do we form a 1? A 1, we usually form it like that, like this one like that, right? So we only have which one? We have the B and the C on. So we have the B and the C on, and the rest of them are zeros. So now, whenever you do use one of these in the lab, we have something that is called common anode or common cathode. It depends on which case you are using. You maybe have to use um, a 1 to turn on or a 0 to turn on. So you have to be careful on that. So now continuing on this, so for example, a 2 would be like this, that, and that one. So all of them on except for the B, except for the F and the C. So F is 0, and which one is 0? F is 0 and C is 0, and the rest are 1s. So all of them are turned on. What about a number 3? So a 3 is like that, right? So we have F and E are 0. So F and E are 0, and like that. So what about the number 5? So 5 we have like this, right? So we have B and E are 0. So B and E are 0, and the rest 1. So you can kind of see what we're doing here. So whenever you complete the table, we only have 0 to 9 digits, okay? So we don't need this bottom part of the table to fill it out. But we do need it when we're doing our K-map. So we're gonna see in a moment. So for this case, actually, for these cases, since we don't need it, we can put this. It's gonna facilitate, it's gonna make our K-maps and our equations at the end easier, right? So I can put a D for all of these because I don't need them, okay? So that's all these, D, 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 D. And you can fill out the rest of the table. And we're gonna see, you can pause it, pause this video, try to fill it out in a paper, and then you can see the answer in a second. So that's a complete one, okay? So now, once we have this complete, and I actually forgot to put all my D's here in this table, okay? But once we have this, we can actually go ahead and design each of these columns, right? This is column A, this is one output. Column C, that's another output. Column D, that's another output. So it's like we have 4 inputs and 1 output. That's the way that you design. So we're gonna do the K-maps for maybe a couple of them. So if we're trying to do the K-map for the A output, so we just have how many? We have 4 inputs, so we have a 4 by 4 K-map. So we have A, and we have like that. And so we just fill it out. 1 0 0 1 0 1 1 1 0 1 1 0 1 1 1 0 1 1 1 1 1, and then we said the rest are these, right? Okay, so now how would we circle this? So in this case, I will probably do all of this. I will probably do all of this, and then I will probably do these 4 maybe, and then let me see what color, other color. I'm gonna do the 4 corners maybe, 4 corners. So the 4 corners. So in that case, I have A equal to, so my red. So red is what? A plus green is what? Green is C plus, we do the yellow one. Yellow one is B and D. And then the 4 corners are A naught. What is this? 4 corners. This row, in this row, what do they have in common? They have this 0 in common, which is the D naught. So that will be the A. Okay. What about the B? So let's do in black. I'm gonna do B. I'm gonna do 0 0 0 1 1 1 0 0. Have A, B, C, and D. I'm gonna fill out 1 1 1 1 1 1 1 1 0 0 1 1 0 0 1 1 1, and then the rest we said they are these. And so we kind of circle again. So that one. What about the green one? What else? We can do this with this side, right? About purple one. Purple, I can do all of these 4, and then this color I'm gonna do all of these 4. Okay, so now red will be my B. B is equal to, actually, and even we can do this plus plus plus. So B is going to be So red, that's just A again, right? And then I have B naught. Remember, this is the green. So the green, this one, what is this? This and this. So that's B naught. And then this one, yellow, C naught, D naught, and this one, C, D. So those are the cases for the A and the B. So in the rest of the cases, the rest of the outputs, you have C, D, A, B, C, D, E, F, G. You can do the same, get K-maps for each of them. And that's how we design the BCD to 7 segment or any other code converter. You have a set of inputs and a set of outputs. You do the K-maps for each of the outputs. So now another example would be to have a binary number and then drive a 7 segment display, but it's also going to go all the way to 16 bits, so hex. So it's going to go from 0 to 15, okay? So the first part is the same as the regular binary to 7 segment. But now if we want to use or display a hexadecimal number in the 7 segment display, we can continue the table. So now remember, in hexadecimal, a 10 is represented by an A, right? And then 11, it's a B, and then we have a C, a D, E, and F in hex. But in the case of the 7 segment, we usually have an A. Okay, we have like that, and then a B, but we do the small b. C, we go like this, a big C. Okay, let me see. Missing one. We can go the big C, or we can go the small. A D, we use the small d, so lowercase d. E is like this, and then F, of course, you have like this. Okay, so this is my E, kind of ugly E. You see, E like this. Okay, and so we're gonna see right now in a moment again. So A, so A, we, so A is capital A, B is small b, then C, D is small d, E is big E, and F. So A, we have everything except for the bottom one, except for the D, right? D LED is off. So that one, my D LED is off, and then I have the rest of them are ones. That's the 10. 11, that's going to be AB, so like this. So all of them are on except for A and the B. So A and B are zeros, and the rest are ones. Now, what about the C? C, I have B, C, B, C, and G are off. So B, C, and G are off. And so you get the idea for this one. Just remember that this one will be a lowercase. Okay. So how would you finish this table? So finish it up, pause, and finish it up, and then come back and see. So this is how would you have it, and then we can use the same process as before, where we have the A, the B, the C as outputs, and we do K-maps for each of them. Now it's going to become a little bit more difficult because we don't have these in this case. We don't have these for don't care. We don't have don't care for the bottom part of the table, but it still can be doable.